Hello friends, welcome to my channel. Let's have a look at problem 2017 grid game. In this video, we are going to share a solution based on dynamic programming or just partial sums. So this problem is a follow-up problem for problem 2483, minimum penalty for shop. So first, I'm going to read through the problem statement to digest the task, and then we explain the observation and do the analysis, and finally we share the short code. First, let's look at the problem statement. So we are given a 2D array called grid of size 2 by n. So each of the elements at position RC is the number of points in that cell. So two robots are playing a game on this matrix. So both robots initially start at 0, 0, and when want to reach 1 n minus 1. So each robot may only move to the right or down, right? So this is actually a key assumption. The reason is that the grid is only 2 rows. Once the robot goes down to the second row, it can only move towards the right. So at the start of the game, the first robot moves from 0, 0 to 1 n minus 1, collecting all the points from the cell on its path. And for all the cells traversed on the path, so the grid, the points is set to be 0. And then the second robot moves from 0, 0 to 1 n minus 1, collecting the points on its path. Note that their paths may intersect with one another. So the first robot wants to minimize the number of points collected by the second robot. In contrast, the second robot wants to maximize the number of points it collects. So if both robots play optimally, return the number of points collected by the second robot. So here are 3 examples. So in example 1, so the first robot jumps down at index 1 to the second row, right? So then all these red points are changed to be 0 after the first robot traversal. And then for the second robot, there are only 2 options: either collect the points in the first row, the tails, or the points in the second row, the prefix sums. So there are 2 passes, either this one, 0, 0, 4, 0, or 0, 1, 0, 0, right? So this is the 4, right? This number 4, because 4 and 1, the maximum is 4. So for the second example, so the optimal strategy for robot 1 is to jump down to the second row at index 0. So the points for robot 2 is 3 plus 1, that is 4. So in example 3, so the optimal strategy for robot 1 is to jump to the second row at index 3, right? So the points can be collected for robot 2 is 1 plus 3 plus 3, that is 7. So before we do the analysis, let's look at the constraints. First, this grid is a 2 by n grid, and the columns is bounded below by 1 and bounded above by 5 times 10 to the power 4. And the point in each of the cell is positive, right? So with that said, we are ready to do the analysis. So here, the key observation is the following. So once the robot moves down, it can only move towards right. So this is very important. So once we realize this observation, so we can do the following analysis. We can assume that the first robot moves down to the second row at position 0i. Actually, this determines the path for the first robot. So here I runs from 0 to n minus 1, both ends inclusive. Then the second robot has only 2 choices. So it either goes down to the second row to collect all the remaining points in the second row. So in other words, go down at the very beginning. So index 0. So this point collected is the sum of grid the second row up before index I. So or the robot 2 can go along the first row to collect all the remaining points in the first row, and that this point is sum of grid the first row and then the points after index I plus 1. So then the maximum number of points for robot 2 if robot 1 plays optimally is the following. So we take the maximum corresponding to each I and then take the minimum. So this will give us the maximum point for robot 2. So if we realize the above analysis, and then writing the code is actually very straightforward. So now let's look at the DP update or partial sum and give a walkthrough for example 1. So in this problem, we just need to consider partial sum, or we can term it as DP. So using the example 1, so this is the grid. So I'm going to define pre-I as a sum of the prefix sum before index I, right, for the second row. And sub I is the sum for the tails in the first row, now after index I, right. Then the DP update rule is very simple. The pre-I equals pre-I minus 1, then plus grid 1 I minus 1, right? Because this pre is the point before index I. So this is before points before index I minus 1. So then we just add the point at index I minus 1. So similarly, we can interpret this DP update rule or partial sum for the suffix. So for this example, the pre and suffix is listed here, right? If we take maximum, we get 9, 4, and 6, and then we take minimum, we get 4. So this is the walkthrough. So next, let's look at the code. So the code actually now is very simple. First, let me get some preparations. First is the number of columns, that is grid 0, right? And then, so let's initialize pre and sub to be 0 length n array or list. So next, so we're going to do the DP update, or we can see partial sum. So it's nothing different in this problem. So what we are going to do is that let's first set for the pre. So for I in range, so I'm going to start from index 1 because before index 0 nothing, so we should keep it 0. So pre-I equals pre-I minus 1 plus grid 1 I minus 1, because we computing pre suffix sums for the second row, and then for the first row, so we compute the tail sums. So we're going to start from n minus 2, then negative 1, negative 1. So because n minus 1, after n minus 1 nothing, so we should keep that to be 0. So sub I equals sub I plus 1, then plus grid, so 0 I plus 1. So this way we finished the update or computing the partial sum, and then we just prepare the return. So for prepare the return, so we can do a while loop, or we can just use list comprehension. See, so we just need to return the max of AB. So for AB in zip, let's see, pre and sub, and then we need to take the minimum of this points, right? So this actually forms the solution format according to above analysis. So here I'm writing this code using ON space. So actually it's quite easy to make it O1 space. We will not do that effort here. So now let's do a check. Yeah, it passes the first example. So now let's do a generic case check. Yeah, it passes all the generic cases. So actually, if you like, you can print out this pre and stuff and to do further analysis. So I guess for this problem, that's about it. So this is also the end of this video. Thank you very much.